Recording. Okay, so today we're going to look at composition of relations, and we'll also do closures, which are on your homework. And if you have done any of the binary relations tutorial, you'll see that it discusses Hasse diagrams, and we'll talk about that a little bit today, but it is not on your homework. It's on homework 10. So we'll leave, because that's whole homework is on graph theory, so we're going to leave a little bit of that for later. And so we're going to look at closures. And I just wanted to mention there were some bugs, definitely, on Lab 4. I apologize. So that was written probably like 10 years ago. And, it used to be fine, but now it's not working as well. So I don't know what happened, but nobody touched it. I will try to fix them. But in the meantime, just remember that you will get credit for spending time on the tutor and not for the answers that you give. So as long as you spend 30 minutes, you'll be fine. Yes? I am going in and programming to let you know, and I went and did that right before class, but I did it for the counting tutorial and not for this one. But when you go log in, after I get it done tonight, there's an option called log out on the main menu, and it'll say log out and time, and you can click on that and it'll tell you how long you spent. Pretty much if you actually didn't just click through the pages, you automatically spend 30 minutes. That's how I set the time, was by looking at people, like the times that they spent, and I could tell if someone was like, if you haven't actually gone through every page on the tutorial, you spent less than 29 minutes. So it was pretty much if you read all the pages, you're fine, because there's like 30 pages and it's about a minute a page to read. Yes? You got a what confirmation? Yeah, like it'll tell you you're done. And it's all recorded. Like every time you're on there, all the minutes that you spend are recorded. So I know that you want a visual confirmation, and I'll program that in tonight. But they're recorded every single time. There is no survey. On the last screen it says, be sure to do your survey. There isn't a survey. So I'll also check that out, but don't freak out. There's no survey. And if you can't log in, just request an extension. And the way you do that is to go to WebAssign and hit extension request. And if you need more submissions, that's the same thing you do. It doesn't say request more submissions. You just hit extension request, and in the comments, just put, I want more submissions, and tell us exactly which thing you want more submissions for. Okay? Any other sort of logistical questions? I just want to thank the peer tutors. Some of you are doing a really great job of like organizing some stuff on Piazza. So I don't remember who it was, but someone actually made a really great post for homework 7, and they listed all the problems, and then they linked to all the Piazza posts that actually were about them. I thought that was awesome. So whoever's doing that, keep doing it, or if you haven't been, you can start doing that. So anyway, if you are a peer tutor, make sure you do log what you're doing so you get credit. So we'll check your log, and then about a week before the final, we will let you know that you're exempt from the final. The other thing is some of you are starting to ask about the test replacement policy, so I just wanted to go over that real quick. It's on your syllabus that you can replace up to 1 test grade at the end of the course. And the way it works is during the final, the final's in 4 sections. Okay, so they exactly correspond to 1 for each test, and then everything we do after the last test. So each test has 3 homeworks on it. The last one just has homework 10. Homework 10 is the easiest homework. And so you'll need to do all the sections. But if you do better on the percent score on that section than you did on 1 section, we will replace 1 grade of your original test for whichever one you did the best. So we'll make a spreadsheet and it'll automatically calculate whichever one you did the best on, and we'll replace your original grade. Yes? Well, if you want to be exempt from the final, but you still want a test replacement, you can come and just take that section. So you don't have to take the whole final. You can just take the section that you want to replace. And if you don't do better, we won't replace your grade. Okay? Any questions about that? Yes? It is the difference. So the question was, it's not the best that you do on the final, it's the difference between the two. It is the difference. So what we'll do is we'll look at every test 1, 2, and 3, and we'll look at your percentages on all three, and whichever one has the biggest difference, we will do that one. I highly recommend that you have a strategy for whichever one you want to make the most points on, that's the one you're really trying to do well on, because people don't do well on my final because it's comprehensive and it has everything that you did all semester. So I wouldn't just be like, oh, I'm going to try to study everything and do awesome on all of them. You should pick which one you really, really want to do well on and make sure you're ready for that. I highly recommend also that you print out, take your tests, anything you missed, and rework it. And even if you got something right but you didn't understand why you got it right, you should come to some office hours and ask. Because if you didn't get it the first time, you're not going to get it before the final unless you ask and get some help. Okay, is that clear? Any more questions about that? Okay. Okay, so I started talking about composition last time, and I said something misleading, so I want to correct it right away. If we have two relations, remember that composition is a way of combining two relations to make a new one. So if I have R1 composed with R2, I actually did it backwards for how we do in the matrix. So I actually have to put the matrix for R2 first. And we do this weird operator for MR1. So this little circle means composition. And it corresponds to composition that you've seen before in math, where you would have something like f of g of x. So that would be written as f circle g, not fog, it's a little circle, f circle g, or f composed with g. But if you notice, in order to do f of g of x, which one do I have to do first, f or g? I have to do g so I can get the output of it so I can figure out what the input for f is. Right? So in the same way, you're actually supposed to do R2 first because they're using the same operator, so they want it to be the same. So in this case, you do g first. So the second one has to be done first. So when we actually represent our relations with matrices, in order to do the right combination of them, we have to put the matrix for R2 first and the matrix for R1 second. So I apologize for the mix-up. Last time I mentioned it the wrong way. So this is the way we have to do it. So R2 is the one that does first, and R1 is the one that applies second. So remember that what we did is a composition says if I have AB in R2, so that was my mistake from last time, I would have said R1, and we have BC in R1, then we have AC in R1 composed with R2. So this is basically the definition of composition. So it's one way of writing that definition, but that corresponds to the result of multiplying two matrices together, but doing it in binary. So at the end of class last time, we talked about the fact that multiplying two matrices in binary is the same process as multiplying them with regular numbers, except for times is replaced with what operation? What does times go to? And plus goes to or. So in other words, you can multiply as usual, and then everywhere you have something that isn't a 0 or a 1, it should be a 1. Okay, so let's do some examples to make sure we know how to do that. So I'm going to do two relations that are on the same set. So all of these are on the set ABC, the cross product of it with itself. Okay, so here's two relations. So this is the matrix for R1, and this is the matrix for R2, and this is going to be R2 composed with R1. So I'd like you to try that matrix multiply on your paper and see what you get. And then we will check it with our neighbor and see if they got the same thing, and if you don't, figure out why. I just wrote down actually how we decide what to put in this position. So what we put in that position is we have to go from A to something in R1, and we have to go from something to A in R2. So there's three different places I could possibly go from A in R1, right? I can either go to A, B, or C. So the way I calculate it is if I go from A to, well, I should have done AA first, so I ended up writing that second. If I go from A to A and then A to A, then that is actually one way to go from A to A where I start in R1, and I start at A and I go to something, and in R2, I go to whatever that something is and get to A. So actually, since I already know that this is true, I can put a 1 in here. So that's because I have AA and AA. But what is AB and BA? So do I have AB? Yes. And I also have BA. So there's another way. So if I did a regular matrix multiply, this would be at least 2, because it will count up the number of ways. So basically what I have to do is I copy over the row that I'm starting with. So I have 1, 1, 0 as the A row, and with ABC. And then I'm going to, for the first column, I'm going to copy over the first column, 1, 1, 0, from my matrix. So this is my row from R1, and this is my column from R2, for the matrix for R2. Okay? And then what I have to do is turn this sideways. So I turn it so A, B, and C go this way, because that's where they are. So this is the A column from R2, and the A row, so this is going to give me the AA element in my composition. So I'm going to turn this, so I have to turn it so the A is on the top. And then I AND all of these. So I get a 1 there, I get a 1 there, and I get a 0 there. So matrix multiply takes a row by a column and combines them all to get a new element for the new matrix. Okay, so it takes this row and multiplies it by that column. So it's element by element multiply, and then I OR them together. If I were to add them together like I do with regular matrix multiply, I would get 2. So in a regular matrix multiplication, it's going to tell me how many paths of length 2 are there between A and A, where the first segment is from R1 and the second segment is from R2. So that's what matrix multiply tells me. And you can see that if I actually added these, I would get 2, right? Yes? 1 plus 1 plus 0 is 2. Okay, good. If I OR them together, I get 1. Okay, so in binary, we would just get, so this is regular, and in binary, we would get 1. Because we're going to use an OR for binary. So that's where we're going to get this one. So let's do the next one. So that's the AA element because it took row A from the first one and column A from the second one. All right, so now we have to do AB. So that's going to take row A, again, is 1, 1, 0, and it's going to take column B, which is going to be 0, 1, 0. Any questions on where I got those rows and columns? So row A is right there. Column B is in the middle. Okay, then I multiply these, or AND them, and then I OR them together, and I get a 1. So now, in the AB element in the composition, I get a 1. This is so not fun, right? That's why we use computers to do this. Because computers will do this and not make any mistakes, right? All right, let's do the next one. So after I do this a little bit, you'll appreciate my magic wand trick. So we'll just keep doing this a little bit. So we need to get the AC element. So we go from row A from R1, column C from R2. Multiply them. I get a 1 and a 1 and a 0. In binary, ORing those together gives me 1. Now we want to do row B. So we want to get the BA element. So we need to do row B and column A. So you can start to see that this element in the composition is telling me which row to take from R1 and which column to take from R2. So I'm going to take that. I'll put 0, 1, 0 for row B, and for column A, I have 1, 1, 0. So I'm going to multiply those. There's a 1 in the middle, and so if I OR those together, I get a 1. You might be thinking we're always going to get 1s, but hopefully one of these won't be a 1, so you'll believe me. We're actually doing something useful. So BB, we have to try row B from 1 and column B from 2. Well, we still get a 1. So multiply each of those. OR them together, you get a 1. All right, so now we want to get BC. We have to do row B and column C. Yet another 1. Okay, we're going to get a 0 on this one. Okay, so now we want to get CA. That's going to be a 1. Can everybody see that? So again, row C, 1, 0, 0. Column A, 1, 1, 0. This one's going to give me a 1. Now CD is where we're going to get a 0. So column B is 0, 1, 0. So if I multiply each of these, I get a 0 in all cases, and those all OR together gives me a 0. And the last one's also going to give me a 1. So I have to take row C and column C. What did I just do? Did anybody see what I did? I copied the row. That's not good. Make sure you write the right thing. So if I OR those together, I get a 1. Okay, so what this actually means is this matrix, the composition matrix, actually is telling me whether or not, I'll get you in a second, whether or not there is a path of length 2 where I start in R1 and take one path, and then wherever I end up, I can start over there in R2 and then end up there. So AA tells me that there is at least one path that goes from A to something and something to A, where the first jump is from R1 and the second jump is from R2. And that's why we have it. It's really cool. And there's a whole class called linear algebra that's about like using matrix multiplications to do whole bunches of calculations at the same time. And if you like this kind of stuff, you should take that class. And if you don't, you shouldn't. Because it's a class on matrices and all the Oh, it's required? Okay, well, have fun. I liked it a lot, but, you guys know I'm a math nerd. So let's see, what else can we do here? Oh, now, wouldn't you like to hear a magic trick to do this faster? Okay, good. Because last time I showed it to you and you were like, we already know how to do that. I was like, oh, you don't need my trick. Okay. So, all right. So here's my magic trick, and it requires a little bit of imagination. And it's the only kind of magic trick I can do. So you have to go to Bitzer's class if you want some real tricks. I can't do them. Okay. So one thing I need to notice is if I take row A and all of the columns of the second matrix, I've turned row A sideways. And now if I sweep it across, I can get 3 values at the same time. So I can get AA, and AB and AC all at the same time if I slide them all across, because a 1 over here is going to pick up something over there, right? So I like to think of the 1s as magnets, and it will pick things up as you're going across. So I like to think of this as a magic wand, and I have a 1 and a 1 and a 0, and when I slide it across, I'm going to pick up 1s with magnets. I won't pick up anything if it's a 0 with a 0. So if I slide this across, I'm going to pick up this row and pick up that row, the entire row. So what I'm going to get is pick that one up, don't pick this one up. All right, so then I'm going to get 1, 0, 1 in the first row, 1, 1, 1 in the second. Then I OR those together, and I get 1, 1, 1. So that gives me the entire first row of 1, 1, 1. So I've done one of those. And so I see that as a magic wand because I can just slide across and tell me which 2 rows I need to OR together in order to get my resulting row. Or 3 rows, or however many. So one other cool thing you might want to notice is that if I have one of my original rows, like C, has just 1, 1 in it, it's going to pick up the corresponding row in the second matrix. So I can actually already go ahead and see that B is going to pick up row 2. So the second row of my matrix is going to be 1, 1, 1. So B, you see when I turn it sideways, it picks up the second row. So as I slide it across, it's just going to pick these up. When I turn C sideways, which row is it going to pick up of the second matrix? Row 1 or 3? 1, because that's the A element. So it's going to slide across here. So my last row is going to be 1, 0, 1. So anywhere I have a 1, I'm going to pick up that corresponding row, and then I just OR together anything that I picked up. And luckily, it matches up with what we did. It's lucky because I could have made a mistake in copying over rows and columns, right? And matrices with 0s and 1s are even worse than regular ones because when you copy them over, it's all 0s and 1s, and so everything looks the same. So it's a little tricky, so you have to make sure you pay attention. So let's do another example using our magic wand trick and see if we can do it super fast. Okay, I'm going to do a really easy one. Okay, can anybody tell what this matrix is? That's the identity matrix. And what does the identity matrix do? When you multiply it by another matrix, it gives you that matrix back. So we know what the answer should be. So let's use the magic wand trick and make sure that it comes out that way. So if I turn this sideways and I have a magic wand, so my blue part's going to be a 1, I slide it across here, I get 101. Now on the second one, my blue part's on the second row, or my 1 is on the second row, so it's going to pick up the second row. And on the last one, I'm going to pick up the bottom row. And that is the same as this one, so that's good because that's what the identity matrix is supposed to give me. Do it again. We'll do it again with a new problem. So this row picked up that one and copied it into here. Row 2 picks up the second row and copies it into here. And row 3 picks up the last row and copies it into there. So the ones pick up things. Because otherwise I'm multiplying by 0, right? All the other zeros in the matrix pick up nothing. They don't result in any ones. Because when I multiply 0 times something, it gives me 0. And then when I OR it, ORing preserves only ones, right? So we only have to pay attention to where the ones go. All right, let's do another example. Okay, so this is going to pick up row 1 and 3. So if I take 1 and 3 and OR them together, I get 1, 1, 1. This one's going to pick up all 3, so I should OR all 3 of these together, and it will give me 1, 1, 1. And this one will pick up nothing, so I'll get all zeros. Questions? Okay, I'll give you another one. I want you to try it, and then maybe we'll have some questions. Okay, so try the magic wand trick and see if you can do this, and I'll give you 30 seconds. Okay, let's check your answer. So row 1 is going to pick up row 1 and row 2 and OR them together, which is just going to give me 1, 0, 1. Row 2 is going to pick up rows 2 and 3 and OR them together, which is going to give me 1, 0, 1. And the third row is going to pick up the middle, which is just going to give me 1, 0, 1. Raise your hand if you got that. Raise your hand if you did not get that. Okay. Raise your hand if you didn't get that because you weren't done yet. Okay. All right. Anybody have any questions that can help clarify? Yes? How do you know which row to pick up? So if you can't do it by looking at it, you should write down the row that you're going to do, the new row. So when I'm in the first row, or row 1, I'm going to make the row 1 of the composition. So I could write that one down sideways, and then I can copy down the entire matrix, and where the ones are, those are the ones I'm going to pick up. So this is going to be row 1. We'll pick up those, and it will OR those together to give me row 1 in the composition. So I'm going to OR this row with that row, and I'm going to get 1, 0, 1 for row 1 in the composition. So for row 2, it will give me row 2 in the composition. If I turn that row 2 sideways, copy over my matrix, and it's going to give me these two to OR together, which will give me 1, 0, 1 as row 2 in the resulting matrix. And then I copy over row 3 in my first matrix, which is 0, 1, 0, copy over the entire matrix for the second one, and that will give me row 3, and it will just pick up the middle row, so that'll give me row 3 in the composition. So if you want to write it over again to make sure you get it right, that's totally fine. Nobody cares. So you don't have to do it in your head. You can write it if you need to. Questions? Yes. Yes. So this is giving me, if this is the matrix for R1 and this is the matrix for R2, then this is the result is the matrix for the composition written that way. It's a confusing thing. So whatever the composition says, I do the matrices in the opposite order. So I put R1 first and R2 second. That means I'm doing R2 composed with R1. So all you need to remember is this, right? So when I do f of g of x, I remember the order is that I do g of x first, so that's why R1 we do first. So when I remember composition, I remember that f little circle g actually means do g first. So same thing for relations. So relations are mappings. That's what functions are, right? Functions are mappings from one set to another. So relations are seen as functions. So that's why they use the same notation as composition in functional math. But we're usually looking at discrete ones, which means that I can actually list out all the rows and list out all the columns instead of like ones for all the integers. So I can't do that with a matrix. So let's do an example with that. Okay, so let's look at two relations where I'm going to say R1 is xy is in R1 if y equals x squared. And I'm going to say R2 is AB is in R2 if B equals A plus 1. Okay, and both of these are on, let's just do these on the integers. So now our question is, what is the composition of these two? So if we're going to do this, we have to go back to our original definition of composition, which tells me that I have to look at the pairs, the ordered pairs that are in my sets. So in other words, let's rewrite this one. So I have AB and R2 if B equals A plus 1, so I can rewrite that as A comma A plus 1. So anytime I have a point, it is of the form where the first number is one less than the second number. So all the points in R2 look like that. And all the points in, so all I'm doing is substitution. So I substituted in A plus 1 for B in the original point that I had. In this one, I'm going to substitute in x squared in my original point. So all of my points look like x comma x squared in R1, and in R2 they look like A comma A plus 1. I just use different letters to notate, like to remind you that we're in different sets for those. But they mean the same thing. They're all integers. Okay? Now, so R2 composed with R1 means start from a point in R1. So every point in R1 looks like this. I'm sorry, that's R2. So we start with a point. Let's just do it on another piece of paper. Okay, so we're going to start with a point in R1. And we want to match it with a point in R2, but it has to have the same number here. So composition said that if we have AB in R1 and BC in R2, then that means we have AC in R2 composed with R1. So all the points in R1 look like this. But if I want to look in R2 to match up points with this, I have to start with the x has to be, the first component has to be equal to x squared. Because otherwise they don't match up for composition. Okay? And then R2 actually says the only points in there are one more than my row component. Okay, so now all we have to do is say, what point is in R2 composed with R1? It's easy because I can just look down here. I can copy the A, which is x, and then copy the C, which is x squared plus 1. So now the composition of these two relations is x comma x squared plus 1. So what you need to do is go back to the definition. So the hardest part about this section of the class is that you do have to memorize the definitions for each of the things, and you have to plug in your relation definitions into our definitions for composition, transitive, symmetric, asymmetric, antisymmetric, reflexive, and all of those. But once you do it, it's not too hard. But you have to practice enough to make sure that you can do it. So by the way, you don't have any homework problems like this, but I did want to show you how you would do it. Questions on this? Yes. Sure. Yes, we can do another example like this. Let's see, we did a square and a sum last time. Let's do so if we want to do R2 composed with R1, remember that we start with R1. So we're going to write x comma 2x. And then remember we have to put 2x here, and then we'll use the definition of R2 to tell me what to put there. So if I have a equals 2x, then we need to figure out what a squared plus 10 is. That's going to be 2x quantity squared plus 10, which is going to be 4x squared plus 10. So I'm going to put that right there. So remember, in our definition of composition, we make a new point with x as the left point and 4x squared plus 10 as the right. So again, I was using the definition of composition as my starting point. And then I plugged in a point that would actually be from R1. And then I started with the first component of something in R2 has to match with the second component of the one from R1, because otherwise composing doesn't do anything. All right, so that has to match. And then once I have that, I can figure that out easily by just using the function that was R2. So this is actually much more directly related to the basic math for this. So here, the function here, this is like having g of x equals 2x, and this is f of x, or a, it doesn't matter, is x squared plus 10, and we just did f of g of x. So now if we have x as an input, we get 4x squared plus 10 as an output. So that's another way to write it, and if you're more comfortable with the functions, you can do that. Okay, so the next thing we're going to do is move on to talking about the closures of a set. And has anybody ever heard of any kind of closure whatsoever? What kind of closure have you heard of? Can you say that louder? Yes, so you've heard of closure under binary operation. Okay, so you've heard of closed under an operation, like so closed under. That's a good point. So that is related. So if I say, for example, we know that the integers are closed under these operations, right? So it's closed under addition, closed under subtraction, and closed under multiplication. Is it closed under division? No, it's not. That would give me the rationals, right? So it's not closed under division. So seeking to have a set that is closed under the division operator is what results in the rational numbers. Because the rational numbers are all the integers plus all the combinations of all the integers divided by each other. So the rational numbers, that's the closure of the integers under division. And so that'll give you an idea of what a closure is. So a closure is if I do some operator on my set, but it gives me things outside of the set, I want to add them to the set so that anytime I do those operations, I stay inside the set. So I'm making a new set. So the closure is usually is a bigger set. It could be the same set. So if I actually asked you for the closure of the integers on the addition operator, you would say that the closure is the integers because it's already closed under addition. So the closure is the minimal set that I take, where I take the original set and then I add whatever I need to make that operation work for all the points and keep in the set whenever I do that operation. So occasionally I've got to add stuff. Sometimes I don't have to add stuff. So if I already have the property I'm talking about, like being closed under addition, I don't have to add anything. But if I don't, I have to add stuff. And so the rationals is quite a lot more stuff, right, than the integers. Right? So even though both of them are infinite, one's like the square of the other one. Okay, so rationals are the closure of integers under division. So there's a few properties of closures. So the closure will so if I take the closure of R with respect to, that's what WRT stands for, is with respect to, and a property. So on the previous one is closed under division was the property. And we'll talk about like reflexive, symmetric, and transitive as the properties we can do closures of. And they are the only properties that we have that we can do closures of. We have to have a few conditions. So the first one is that, let's call this RC for closure. Okay? So the first thing we have to have is that R is a subset of RC. So it has to have everything from R in it. Whatever was in the original relation, it still has to be in there. Okay, now RC has to have the new property. And the third thing that we have to have is that RC is minimal. Does that mean that RC is small? No. It means I didn't add any extra stuff. So for example, if we went back to the integers example and we said, tell me what the closure of the integers with respect to the division operation is, and you said it's the real numbers, you've just added a whole bunch more stuff that doesn't actually need to be in there to make the integers closed under division. So it is not a closure because it is not the minimal amount I have to add. How many of you have done anything with limits? Okay, so you've done things with limits, right? When we are looking at a series, like normally we're taking the limit, we're looking at a series like of divisions maybe, and we try to figure out what that limit actually is, right? So, for example, 1 over n. What is the limit of that as n goes to infinity? Okay, the limit is 0. Does it ever reach that? No. But if I took the closure of that series, then it would actually reach it. So I would include 0 in a closure of that, so that all the limits, whenever I take the limit, it includes whatever would be the limit. So we do it in a lot of other kinds of math, but we're just going to do it here because there are a few properties that we'd like to do this for. So when I ask you to, a couple of your homework problems ask you to show that certain things are the closure of other things with respect to certain properties. So we're going to see how we can do that. Okay, so the only closures we can do are reflexive, symmetric, and transitive. The reason is because if I wanted to do the antisymmetric closure, I would have a problem, because usually something is antisymmetric. Remember that antisymmetric says so in your relation for all x and for all y, if I have xy in the relation and yx in the relation, then that means x and y have to be the same. So if something's not antisymmetric, can I add something to make it antisymmetric? I can't, because if it's not antisymmetric, then I have something like this. Because the only way for this to be false is what? This has to be true, and that has to be false, right? For some values of x and y. So if something is not antisymmetric, it has something like this, and x doesn't equal y. So over here, it is true, but over there, it's false. And I can't add anything to fix that. I have to take stuff out. And closures are not allowed to take things out because of the first property of closure is that it has to have the original set in it. And so if these points are in the original set, there's nothing I can add to make it antisymmetric because I can't take things out to do a closure. So that's why we can't do antisymmetric closure. We can't do asymmetric closure. We can't do irreflexive closure. None of those. We can only do reflexive, symmetric, and transitive. So remember that the property for reflexive is, for all x, the point xx is in the relation. So that's not hard to fix. If you don't have them, you just add them. Right? So if I have a relation that doesn't have all those, I just add them. So I can define a set so I'm going to call this E. So what does the matrix for E look like? It's the identity matrix. And reflexive, remember that reflexive actually said we had all ones on the diagonal. So if something's not reflexive, I just OR the matrix for the identity matrix with my original relation, and then it's reflexive. Because all I need to have is all ones on the diagonal. So if I make a set that has all ones on the diagonal and I OR it with my original set, then I'm there. So if I have R as a relation, if I take the union with E, then this is the reflexive closure. So let's prove it. This is one of your homework problems, by the way. So we have to prove three things. We have to prove, one, that R is a subset of RC, and RC is equal to R union E. Is R a subset of that? Yes, because the definition of union. Union says add the stuff for both of these. That doesn't delete anything, so everything in R has to be in R union E by the definition of R union E. So let's remember what the definition of R union E is. R union E equals the set of xy where xy is in R or xy is in E. So every single point, so therefore if xy is in R, then xy is in R or xy is in E is true. So therefore xy is in R union E. Questions about that? So usually when we do the closure, the first thing to prove is really easy because we add stuff to the set and we just say, hey, we didn't take anything out. Therefore, the set's still there. Okay? The second thing we need to do is to show that our new set is reflexive or has the property that we're trying to do. So, what's the definition of reflexive? So, reflexive is for all x, xx is in the set. So, this is what I have to prove. But E, remember, was precisely all of these sets. So whatever set R is in S cross with S, then XX is in there. So, since E is a subset of R union RE with the same argument that we had before, by the definition of union, therefore R union E is reflexive. And we should be able to prove this because we picked out the set. Now the last part is the hardest part. We're going to do it by contradiction because that is the only way to show that something is the smallest possible. So if it's not minimal, what that actually means is there's an extra point in there. So that means I could take a point out and it will still have R as a subset and still be reflexive. So the negation of the conclusion is that there exists a point xy that's in RC so that RC minus the set containing xy contains R and is reflexive. So that means there's a point I can take out. That's exactly what that means. Well, RC is equal to R union E, right? So if I have a point in there, it either has to come from R or it has to come from E. So we have two cases to prove because we have to prove it for all possible points xy. So we have two cases. So case one, so because of the definition of union, if I have xy is in R union E, then xy had to be in R or it had to be in E. Because it can't come from anywhere else, because that's the definition of union. I can take all the points from R and all the points from E and no other points. Okay, so case one, we will look at xy was in R. If I take RC and I take out xy, then that means that that point, xy, is no longer in the closure. And that means that R has a point in it that the closure doesn't have. And that's wrong. That's a contradiction. We can't have that because that was part of our assumption in the negation of the conclusion. So what we're going to have right now is xy is not in the set RC minus xy, but xy is in R, and R must be a subset of the closure. So this is a new closure. Let's call that RC star. So that's a new one, and that's why you see proofs That's why you see in math proofs, you see like a little star or an apostrophe on a set when you do something to it. It's because they're like, it's almost that set, but I took something out. So in order, so this is a contradiction. Okay, so if I take the point out of R, where it came from originally, then it doesn't work. And case 2 is going to be exactly the same. So except that it's going to break the reflexive property. So xy came from E, but the definition of E tells me that that is x equals y. So actually we have xx. So RC minus XX, so we're going to make a new RC star. RC minus XX is going to have a problem, right? It's not going to be reflexive. So in both cases, I have a contradiction. And so therefore, we're done with the proof. RC is minimal. R union E is the smallest possible closure that we can make. Because we can't take any of the points out. If we do, we break one of the conditions we have to have for the closure. Now, by the way, you have to do both of the cases. So this is like the proof that that we did, the arithmetic proofs where we said 3 doesn't divide a function for all of the integers. You can't just stop when you find one row that's false. Okay? You have to do the entire table. So we have to do all the cases of all the numbers. And so xy comes from R or xy comes from E. I have to do both of them and tell you why I can't have either one of those. Okay, so we're done with that. The symmetric closure works very similarly, and the proof is almost exactly the same. There's one notation you need to know so you can do it. So if I have R, then R inverse is the set of xy where y comma x was in the original set. So basically I'm swapping the rows and columns, or I'm swapping the elements to make R inverse. So the symmetric closure for a set is R union R inverse. And your proof of it will be exactly the same. You'll say, well, R has to be in there because it's a union. And then R inverse makes it symmetric because everything that had an xy in R now has a yx in R inverse. It does have its opposite. And also anything that came from R inverse has its opposite in R. So you actually have to do both. So for proving that it's symmetric, you have to show that all the points in there, so all of these points, so those points have their opposites over here, and these points have their opposites over there. And then when you're showing it's minimal, the same thing. You say I can take a point out, but then you say if I take a point out, it either came from R or it came from R inverse. If it comes from R, I break the requirement that R has to be a subset of the closure. If it comes from R inverse, I break the requirement that it has to be symmetric. So I'm not going to do that one because I want to tell you about transitive closure, which you don't have to do on your homework, but you still need to know what it is because you have to be able to find a transitive closure. I'm not going to make you prove it because it's hard. The reason why transitive closure is hard is because you have to do a whole bunch of stuff to get it. Now, the first thing we need to do is to give you a couple of definitions. One is that R is transitive is logically equivalent to saying that R squared is a subset of R. So we talked about composition today, so R squared is equal to R composed with R. So you need to know that. R squared is equal to R little circle R. And that means that you square the matrix for it. So why does this work? It works because the definition of transitive and the definition of composition look exactly the same. Right? So the definition of transitive says for all x, y, and z, if x relates to y, and that's in R, and y relates to z, so let's do, yeah, that's fine, just R. And if that's in R, then I have to have xz is in R. So that's the definition there. And for composition of so there's the first definition. So there's the definition of composition that tells me how to make all the points, R1 composed with R2. I'm wrong, sorry. That's R1 right there. That's R2. Okay, so there's the definition, but if all of these are R's, so if R is composed with R, then these are the same things. So that's just R, and that's just R, and this is R squared. If R1 equals R2 equals R. So if something is transitive, xz is in R, but we already know that xz is always in R squared, no matter what. So if everything that's in R squared is actually in R to begin with, then we know that our relation is transitive. So that's actually how you test whether a matrix for a relation is actually representing a transitive relation. So in order to test whether a set is transitive or a relation is transitive, you need to square it. Like you have to do all the possible pairs and see if they need to make new points or not. So that's why matrix is really nice for that, because now we have a magic wand trick, so we can do matrix composition a lot faster than doing all the pairs comparisons, because it's very easy to miss stuff with that. So the transitive closure, the first thing you might think is, okay, if I don't have all the points in my set, I could get the closure just by taking R and then unioning R squared with it. The problem is now the new points that came from R squared have to be tested with all the points from R to see if they make any new things. So I have to see actually if there's a point like AB in here and BC in here, I have to make a new AC. But that point comes from R cubed. But then I have to do R cubed with all the other ones. So I also need to union it with R4 to do it with these two, and R5 to do it with those two. Oh my goodness, it goes forever. So the transitive closure of a relation is the union, k equals 1 to infinity, of R to the k. Now you don't have to go to infinity usually. You only have to go to infinity if your original set has infinitely many points. Otherwise, if you have a finite number of points, you only have to go up to the number of points. So k only has to go up to the number of original points in S, where your S is the set that you're doing the relation on. And the last thing you need to know, and I apologize for running a little bit late, but I do need to tell you one more thing so you can actually do the closure proof or closure problem on transitive closure. So what you have to prove in your homework is that if R is transitive, that implies that r to the n is transitive. So you have to prove this by induction. So the basis is easy because r to the 1 is just equal to r, and that's transitive, that's a given. So that's what you need to prove. And you need to remember that the definition of transitive means that r squared is a subset of r. And you also need to know that if A is a subset of B and C is a subset of D, then A composed with C is a subset of B composed with D. So, and you could call this the class lemma. And that's what you'll use for that. I understand some of you need to go. I'm going to do a little bit more for those of you who want to stay. So if you want to go, that is fine. But we'll talk about how this works. No. So this statement, in order to do the proof, I copy it over and I put an n plus 1 wherever I see an n. So I don't actually do that. So I'm going to assume that if r is transitive, then r to the n is transitive, and I need to prove that if r is transitive, then r to the n plus 1 is transitive. I'll just work it. If you need to go, go ahead and go. So what is r to the n plus 1? It's r to the n composed with r, because the powers are the same as how many compositions got done of the original set. So if I want to say that r to the n plus 1 is transitive, I have to use the definition that told me that the square of this thing, whatever it is, if I square it or compose it with itself, if I compose it with itself, then it has to be a subset of the original set. Okay, so instead of running even more over, I'll post something about this on Piazza, but basically that's what you need to do. And you're going to use this. So that's what the assume means. And this is what the prove means. All right, thank you guys.